Welcome to the fifth live session of Quantum Topology 1 NPTEL course. So, till last live session, we have gone through the connectedness thing. And in this session, my plan is to go with the compactness. And well, the chapter compactness is very big. So, possibly it will take a two lab session. And after finishing compactness, there is some interesting, namely evolution matrix extension theorem and all that, which ensures the existence of a topology in a given, existence of metric space in a given topology of a polygon topological space. So, okay. So first, let's start with the definition of compact set, and let's see how much we can do in today's live session. Okay, it will be 2 hours live session. If you have any doubt or any question, you can ask me in between the live session. Okay, or you can do an email to me. I'll get back to you. Okay. So let's start. Okay. Yeah. So yeah. So let's start the definition. So okay. So let X be space. So let X be space. X is said to be Okay, sorry. Okay, so there is some definition, something open curve first. We need to give that. Okay, so definition. So what does it mean by open curve? Okay, so a collection U alpha of open subsets of space X is said to be an open cover if X is nothing can be written as union of U alpha. Okay. So what is an open cover? A collection U alpha. Collection of what? Collection of open subsets of X is said to be an open cover if X can be written as union of U alphas. Okay. So for example, if we take the real line, then the collection minus n comma n, this collection forms an open cover. Obviously, of course, this open cover is not necessarily unique. Because why? Because so so n plus 1, this also forms an open cover. Okay, so this is the definition of open cover, that is a collection of open sets which covers whole of X. Okay, then what is the definition of subcovers? So let X be a space and this collection be an open cover. and let the U alpha be an open cover of X. Okay, so a subcollection of this collection U alpha is called a subcover. Okay, so what is subcover? Subcover is subcollection of the open covers. So that's a subcover. So now now it comes the definition. Compactness is the following. Let X be a compact space then I'm sorry, let X be a space. Then X will be say then X said to be compact if every open cover has finite sub. A space X said to be compact if every open cover has a finite subdivision. What? That is, for any open cover U alpha of X, there exists alpha 1, alpha 2, alpha n such that X can be written as union of U alpha I is equal to 1 to X. So there is a finite subcover. So in a space is said to be compact if every open cover is a finite subcover. Okay. Kindly wait. Let me check one thing. Once. Yeah. So this is what is it? Every open cover is a finite subcover. So let's just an example first. So take X equal to R. Okay. And consider the open cover U to be minus n comma n belongs to n. Sorry, n belongs to n. Check that it does not admit a finite So how to approach? So what we have, so we have x equal to 1 and we have some u is equal to collection of minus and n, and we need to show that this does not have a finite scope. This is what. So basically, I mean, look, I mean, obviously it is not possible, at least intuitively, because it is minus 1 1 minus 2 2 minus 3 3 dot dot dot. So anyway, it can't have any finite thing, something like that. So that's a possible. So but we need to prove mathematically. So how to start with? So suppose, wait, let me check some other problems also. So suppose, so let that collection UN admits of finance. Okay. Let this file isolate with UN1, UN2, UNK. Okay. By the way, here I mean was the minus icon. Okay. So take choose jump to be maximum of all these things. Okay. So then what? Then what are getting? We are getting a union of even I is equal to 1 to k is equal to minus m plus. And of course, it is not equal to whole of R. So any finite subcollection can't cover whole of R. So this is it. So this is the full argument. That is, so this is what? So the real line is not compact. Okay. So this is one example. Now, once. Hmm. Now once. Yeah. Oh. So okay. So consider the try to solve this. Let x be a finite set with cofinite topology. Show that X is compact. So X infinite is cofinite. We need to check the X is compact. So how to do? So first we need to realize what are the possible ways to solve this, right? So what are the possible to do this? So so we need to show that it's compact. So we need to start with an arbitrary open cover. We need to somehow come up with the conclusion that it is a finite subcover, right? So let's start. So let U alpha be an open cover of X. Sorry. So consider U alpha naught. So U alpha naught is an open set in X. So this is what? This implies X minus U alpha naught is a finite set, right? So let this set contains x1, x2, some xk. Now since X is an open cover, sorry, U alpha is an open cover, so we can choose xi to belongs to U alpha I. So then what? So then U alpha 0, U alpha 1, U alpha k is a finite subcover of X, right? So this is what the argument is, correct? So if the space requires with the cofinite topology, then any space is compact. So with cofinite topology, infinite set is compact, okay? But if we change the topology co-countable, it is not necessarily compact. So let X be an uncountable set with co-countable topology, then X is not compact. So how to do? So, I mean, we need to somehow come up with a particular choice open cover which does not admit a finite subcover, right? So, what are the possible ways? Of doing it? So, I mean, so yeah. And so, remember one thing that in co-contour topology, what are the open sets? So, all those sets will open if and only if its complement is countable, right? Correct. So, it's a co-countable topology. So, the trick is the following. So let's choose a sequence x1, x2, x3, xn. It's a countable sequence inside x, and put u1 to be x minus x1, x2, x3 dot dot dot. u2 to be x minus x2, x3 dot dot dot. u3 so dot dot dot. un to be x minus xn plus 1 dot dot. So clearly this ui's covers the whole of x, but the claim is, so this is an open cover of x, but claim it does not have any finite subcover. So how to do? Oh. So look, so I mean, so okay. So what are the possible ways to do this, or what are the possible way to prove this? One second, kindly wait. So suppose let this open cover admits a finite subcover. So let this open cover admits a finite subcover u n1, un2, un. Okay. So then what will be union of u and I is equal to 1 to k? This will nothing but x minus xk, xk plus 1 dot dot dot. So of course, so xk does not belongs to in this union. So this, so it can't admit any finite subcover. So that's why, so so any infinite set it co-countable topology not compact. Okay, so this is the argument. So well, let me just find the next thing. Okay, Wait. Mm. Okay. So, well, that's fine. So, okay. So, the next is now the following. One second. Show that. One second. Let me ask you back of 2 minutes. আচ্ছা রাতে আর ভাত খাওয়া দাওয়া না বুঝলে so the question is that show that uh, open zero closed one of course with usual topology is not compact. So we need to prove that open zero closed and not compact. How to do this? না না একটু না এখন রাখো so what we need to prove is the following. We need to somehow construct an open cover which does not admit a finite subcover, right? So, what are the possibilities? So, till now, actually, we don't have enough tool for doing this, but uh, what we can do is the following. So, we first initially try to construct open cover and try to figure out a finite sub for the following, right? Okay. So, let's start with an construct an open cover. Okay. So, so okay. So, okay. So, consider the following open cover. Let's see. Yeah. Open 1 by n closed 1. This is an open cover of open 0 closed 1. Okay. I mean, it is obviously open cover because 0 belongs to whole union, right? So, anyway, it's not a big deal. So, anyway, the 0 belongs to union because of the Archimedean property. 0 belongs to here due to Archimedean property. Okay. So, oh, so, so it does not a finite whole integer. So suppose assume that this admits a finite subcover. So let's assume that it admits a finite subcover. Okay. So we have some, and I call this thing UN. So we have some UN1, sorry, UN1, UN2, daughter, UNK, such that these their unions is equal to whole space 1, right? So now what we will do is the following. So we will take M to be max of N1, N2, Nk, and then what we'll get? We'll get a union of Ni, I is equal to 1 to K is equal to 1 by M comma third bracket 1, and of course 0 does not contain here, so this means what? So it does not admit a finite subcover. Okay, correct. So yeah, so this is the argument. So open zero closed one does not have a finite subcover. So from this question, you have observed one thing is that the only reason of being non-compact is that we have openness in the zero side. Okay, so you might possibly guess that if a closed one it is compact, and if you are guessing it, then you are correct. So it's a theorem. It's a remarkable theorem. And it's a remarkable theorem that in metric spaces, closed bounded as a compact, but since this course is not a metric space course, so right now we're not getting into this directly. We will see these results, but first we will see some results that come from topology, then we'll gradually get to the metric space. Okay, but believe me, in metrics there are some very beautiful results. Okay, so wait, let me check some new thing. Wait, kindly wait for 1 or 2 minutes. So, okay. So now, okay. So till now, one second. So till now, what we have seen. So till now, we have seen the definition of compactness, and we have seen some examples. But the point is that definition of compactness comes into the open set. We choose that open to open in the whole space. So one may ask about what the definition of compactness in case of subspace. So the same definition will work in subspace also, but there are some, but due to some theorem, the whole. So I mean, so suppose you have a lemma. I mean, so we have the following lemma, which directly talks about the yeah. So this lemma is the following. So sorry. So let Y be a subspace of X. So this lemma says the following: that Y is compact if and only Y is compact if and only if. So Y is compact if and only for any open cover U alpha, open to U alpha such that Y subset of union U alpha. Oh, sorry. in an U alpha, here exists finite subcollection alpha around where such twice our union of U alpha and is going 1 to n. Okay, so these are so I mean so then I mean well you can try to also in order to access open function y is of the unit section of y has user open x. The thing is if we need to check comes with compare we can consider y to be set. To alpha we need finite collection or is not. That's all it is, okay. So this concerns about checking compactness of subspaces. So now we have some theorems. These are the following. So the first theorem is that everyone. So closed subspace of compact subspace is compact. Uh, every closed subspace of compact space is compact. So how to do? So what are the ways in by which we can attack this problem? Once, please wait a minute. Oh, yeah. So once. Oh, so 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 let x be a compact space, okay, and let A be a subset of X and assume the closed subset. We need to prove that A is compact. So how to prove? How to do? So what are the possible ways to do that? So let's okay. So let A is a subset of union U alpha or U alpha is open in X. Now observe that this collection U alpha union X minus F is an open cover of X, obviously. So it admits a finite subcover. So this is what? So this union U alpha I is a finite subcover of X. So this is what? So the set A lies inside U alpha I is equal to 1 to n. Okay. So now, okay. So this is what. So any closed house, only closed house is compared to the compound, right? So this is what we try to prove, right? Okay. So the next thing is the following. Every compact subspace of Hausdorff space is closed. So how to do? So okay, think about it as a backwards. Ah, hello. ನಾನು হাত দিয়ে এখন কাটাতে মতো হ্যাঁ ছাড়িয়ে দাও না তাহলে সেটা ভালো হয়। তাহলে ছাড়িয়ে দাও আমি তাহলে আসবো তাহলে না না দিয়ে আসতে হবে না আমি নিজে আসবো এই ঘরে এখন আসবো না আমি নিজেই নিয়ে নিচ্ছি ওটা একটু করে হাবিবি আল্লাহ হাবিবি so so what we need to prove the following every compact house with a house door is closed so how to prove this So let okay. So we need to start with the house rules, right? So let X be a house of X, right? And A be a compact house of X. We need to show that is closed. Okay. So it is equivalent to showing that X minus A is open, right? Whatever it is. So what we are doing, we shall do the following. So choose any point outside capital. Okay. And choose A belongs to. Being house drop, there exists an open set U containing X naught and an open set VA containing A such that U intersection VA empty. So this means what we're getting, this is our X and this is A, and we are choosing one point X outside A, and for each A belongs to A, we are getting one open cover here and one open set here, not intersection. So what we are doing is that we are choosing this VA, A belongs to A. This covers capital A. Okay, and we are taking W to be intersection of U. A belongs to A. And this contains the X naught. Okay. Now since A is compact, so it admits a finite subcover, right? VAI belongs to N, right? So now, if we take capital V to be union of VAI, then of course, this set W intersection A is equal to empty. Because if W intersection A non-empty, this implies what? W intersection union VAI non-empty. This implies W intersection VAI non-empty for some II, right? But by our choice, W is the intersection of this VUAI, then these are here as empty. So the intersection as a whole is non-empty. Okay, so this is the argument. Okay, so this tells that every complex substrate horizontal is closed. Fine. Next. So, let me check the next thing. So the argument is the following. So yeah. So okay. So finally, what I've seen is the following. The compacts as a house was closed, right? So now next. So this thing have the following corollary. So I mean, if we go through the proof of the above theorem, so we realize that um, yeah, we'll realize that. I mean, this is not a corollary. This is actually a lemma. I mean, a graceful lemma. So it's the following. So let Y be a compact subspace of Hausdorff space. T2 means a Hausdorff. Okay. X and X naught lies outside of Y. Then there exists disjoint open sets U and V of X with containing X naught and Y respectively. So means what? Suppose we have a compact also given also of X and suppose X naught lies outside of Y, so we are able to find open set U containing X, open set V of X containing Y as they are disjoint. So this is a very useful lemma. Okay. Okay, so the next theorem is the following, like in connectedness. One second, yeah, like in kind of we have seen that continuous maps and kind of things connected. So in the same thing goes to compact thing. I mean, continuous maps and compact. The still following. The theorem is that the image of not what image continuous image of compact space is compact. Okay. So, so think about it. I should back after some minutes. Okay, let me search the next theorem. Actually, wait a minute. Okay, so image of compact space contains a compact compact. So suppose a from x to y, the continuous. Okay, and let x be compact. We need to say if x be compact, right? So what we'll do? We'll write fx as union of u alpha. So this will be what x equal to f inverse union e alpha is equal to union of f inverse u alpha. So this is the collection f inverse u alpha forms is an open cover of x, right? So it admits a finite subcollection. So then this is what x equal to union of f inverse u alpha I. And one to this is what fx subset of union of u alpha I is equal to 1 to n. So finite subquad. So this is what this is fx is compact. Okay. So under continuous the continuous map sense compact space to compact space. Okay. And it gives rise to the most important theorem which we shall use. I mean, the theorem which I am now going to state is not as this can be think exercise, but anyway, this should be think as a theorem also because this type of applications are very pretty common in in problem solving. Okay, so let's yeah x to y with bijective continuous function. Now, if x is compact, y Hausdorff, then Yasuda, homeomorph. So how to approach this problem? So it is given that x is compact to y Hausdorff. So what are the possible ways to solve this problem? So wait. Oh, the screen is smaller. What's kindly wait. Let me. Okay, yeah. So so look, it's a bijective and continuous. Okay, so we need to say inverse of it. So we need to check that it's closed loop. That's also it can be right. So what we do is the following: x given to x to be given compact. Okay. So start. So we will try to show that f is a closed map. Okay. So start with the closeness. So let it be a closed subset of x. Okay. Now x is compact, so this implies b is compact in x. Okay. Now if it's continuous, this implies if b compact in y. Now y is house drop, so this implies what? This implies if b closed in y. So this implies f is a closed map. So you're done. Okay. So any contrast map from a compact, any Bayesian contrast map from a compact space to Hausdorff space will be a homeomorphism. Okay. So the next theorem. Correct. So the next theorem is the following. So the next theorem is so there is one theorem known as tube lemma, but right now we are not going into the proof of tube lemma. Okay. So initial first we shall first try to solve the theorem. Then, if time permits, we shall go with the tube lemma thing. But right now, let's get into straight to the fact that product of finite product of compound is a compound. Okay. So theorem is follows. That is finite product of compact spaces is compact. So, well, I'm not going to going through this proof right now, but anyway, finite product compact is compact. Just keep this thing in mind. After finishing all the rest of the things, we shall get in the proof of this things. Okay. So, finite product compact is compact. Okay. So, this is one very important. So, now there is one concept. So, okay. So, till now we have checked different ones. Okay. So yeah, till now we have checked different ways to check the uh, compactness of the given space, right? Now there is one another process. Well, that process is quite different from the others, but that might be sometimes useful. So let's get into this. Okay. Okay, one more thing is that we have mentioned that finite product compared to compact. Actually, the same is true for the infinite product, but that is the proof is entirely different, and that is known as the Tychonoff's theorem. Okay, so these things will come into the end of this course. Right now, we are not going into these things because our main target is to try to understand basics and to solve problems as many as we can. Okay, so we have some following definition now. So what we are trying to, what we are going to see in the rest in the last 1 hour is the is another criteria of checking compactness of given space. Okay, so let C be a collection of subsets of X, and this is said to have finite intersection property if any finite subcollection C1, C2, Cn of C the intersection C1, Cn non-empty. Okay. So, what is the finite property? See the collection of set of finite property. If any finite subcollection, find the section is finite subcollection, its intersection is non-empty. Okay. So the theorem is follows. Let X be a space of a topological space, then X is compact if and only if once. Wait. 2 minutes. Can you wait? Well. So okay. So the thing is, x greater than x is compact if and only, yeah, if and only for every collection C of x and collection of closures of this. So closure of C of x having FIP, this finite property has non-empty intersection. So the thing is what x is compact if and only for every collection C of x having finite property has non-intersection. Okay. Okay. So how to prove this? Hmm. So let's see. Okay. Well. Okay. So I mean, I was thinking that I'm going to prove it, but anyway, it's better that if you can try it by yourself. So I mean, if you can't solve it by yourself, please let me know in the next live session. But for today's for today, I'm not going to prove this. Okay, you please try it by yourself. If not done by you, please ask me in the next live session. Okay. Okay. So now let's start with some problems. Kindly welcome back to some lessons. Oh well, correct. So, okay. So, let's not problem. Okay. So, hmm. So now let's start some exercises. Let tau and tau prime be the topology. Suppose tau prime contains tau, then prove that either tau, prove that either they are equal or not comparable. So what it we know, so we have to topology tau and tau dash to prove that is equal and not comparable. So how to do? So let they are comparable, okay, and let tau become tau dash. So consider the identity map x tau dash to x tau. Okay. So it is continuous. Obviously it is bijective, and the space X is given to be okay. X is given to be compact plus Hausdorff. Okay. So now this I mean this domain is compact and the code of Hausdorff. So this is what the I is a homeomorphism. The identity map is a homeomorphism. So this that's the topology tau and tau as the same, right? Yeah. So this is what we need. So okay, so this is the problem. So let's okay, so this is the one theorem. Show that finite union of compacts is compact. So how do we think about it as a back? আচ্ছা বক্তব্য যে ম্যাগি খেতে পারবো কি? ম্যাগি খেতে পারো? ম্যাগি খেতে পারবো কি? ও ও আচ্ছা নাও রয়েছে নাও নাও। হ্যাঁ আঙুর খেয়ে নিয়ে এসে দিল আঙুর দিয়েছে। হ্যাঁ নাও। আর কালে কি হবে, মাংস না মাছ? ঠিক আছে নাও। আহ, অন্য কটা না না এখন না, দাঁড়া কথাটা শোনো না, আমি অনলাইন ক্লাস করেছি মাঝখানে গ্যাপ আছে, ফোনটা বলছি। না কিছুটা লাউ দেখে রান্না করে দেখেছি তো, কিছুটা দাও লেখা আছে তাহলে কেন? হ্যাঁ তো তুমি তো বলেছো, তুমি তো বলো দই কম খেতে। আরে গর্ধব, তারপরে তো তুমি কথাটা বললে না যে অতগুলো দই খাওয়া যাবে না, তারপরে তুমি কমিয়ে দিও, ওই কারণে তো দই কম দেবে। ইডিয়েট, ওটা আমি প্রথমে বলেছিলাম যখন প্রায় গোটা 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 বই দইটা আমাকে দিয়ে দিত যখন প্রথমে। পুরো- প্রথমেও প্রথমে গোটা দইটা, তারপর তুমি বললে কম খেতে হবে। এটা হচ্ছে বিষয় আমাদের গুলো। আর তার থেকে বড় কথা হচ্ছে আমি অর্ধেকটা দই হলো আমি সকালে অতটা একসাথে খেতে পারি না, কারণ অ্যাকচুয়ালি অতটা দই অনেক টাইম লাগে, এবার দই আর মুড়ি তো খেতে অনেক টাইম লাগে ওটা খেতে। তো ওই কারণে সকালে অতটা দই খাওয়া যায় না, ওইখানে যদি খেতে হয় তাহলে কি দুপুরে বাকিটা খেতে হবে। তুমি তো পরে তো বলেছো যে দই অত বেশি দেওয়া যাবে না, ওই কারণে দিতে হয়নি। কে বললো? না না না, ওটা তোমার মনে হয়। বেশি জ্ঞান দিবে না সব ব্যাপারে। আমার এমনি সকালে দই খেতে বিরক্ত লাগে, দই মুড়ি খেয়ে বিরক্ত লাগে সকালে এমনি খেতে। রুটি 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 খাওয়া, রুটি মেরে পেটও বন্ধ হয়ে যাচ্ছে। আরে দেখ গাধা, আমি দই ভালোই লাগছে না, দই তো খেয়ে যাচ্ছে এত যুক্ত। সকালে তো হবে না, তাতে দই মুড়ি খাওয়া সকালে, সকালেও সবজি মুড়ি রান্না করা যায় নাকি? পাগল নাকি? ও ভালো করে লাভ নেই, সকালে ওসব খাওয়ার লাভ নেই, তাতে দই মুড়ি। আরে আরে দই আর মুড়ি এই দুটো জিনিস বাদে অন্য কোনো জিনিস খাওয়া সম্ভব কিনা সেটা বলো। মুড়ি আর দই খাওয়া যায় নাকি সবসময়? সকালে ম্যাগি খাবো এটা বলিও নি আমি। না না, ছাড়ো বাদ দাও, যাও। হ্যাঁ তা তো বটে। হ্যাঁ বুঝছি, মাথাটা বুঝছি। না না, থাক, তাহলে 2 মিনিট থাক। ছাড়ো বাদ দাও। আরে দেখ না, আমি অত এক্সপেরিমেন্ট করতে পারবো না বসে বসে। আরে দেখ ওসব না, অত এক্সপেরিমেন্ট করা দরকার নেই, যেটা আছে সেটাই থাক। এটা হচ্ছে ব্যাপার। আর দই মই যদি বলো অর্ধেক দিতে, যতটা দেয় বাকিটা এক্সট্রা দিলে ওটা দুপুরে দেবে, সকালে অতগুলো খাওয়া যায় না একসাথে। আর দরকার নেই। আরে দরকার নেই ওসব। ও সকালে সবজি করবে নাকি? ও নিজে 8টার সময় উঠে ও কেমন করে সবজি আসলে তাতে বড় কথা না, আমি সকালে আলু বোধ খাওয়ার পছন্দ করি না। আমি এক্সপেরিমেন্ট চক্করে পড়তে ভালো লাগে না। না। ও। So, what do you need to prove that finite and complex is compact? Okay. Okay. So, so we will do this for two complex house. So let X be a space and let A be R. Compact subspace surface. Okay. Correct. So this is compact subspace. Okay. So so we need to show that A union B compact. Okay. So we'll try to write A union B sub a union, sorry, subset of union U alpha. So of course A, B are sub of union U alpha. So this A complex, A subset of union U alpha I is equal to 1 K, and B sub of union uh, E alpha J is equal to L to M. So this is A union B is sub of union of E alpha I is equal to 1 to M. So this implies A union B is compact, right? So these implies A union B is compact. So this is what we need to prove, that if you find a union compact, so it's compact, right? So that's also this is it. Okay. Hmm. So there is one question following. So let A and B be disjoint, compact subspace of Hausdorff space A. Sorry, Hausdorff space X. It is not A, it is the X. Okay. Show that there exists disjoint open sets U and B containing A and B respect. So what is the so basically we have some space X and we have some two compact subspace A and compact set B. We need to show that we can find an open set U and B such that the intersection is joint. So how to proceed for solving this? So we have seen one theorem, namely if any compact subspace, so y x belongs to y in a compact subspace, then x naught b belongs to outside of y, we can separate that point and the compact set by means of disjoint open set. Right? So we are going to use that thing here. So what we'll do is the following. So we are taking A belongs to A. Okay. So there is open set UA containing A and VA containing X minus. Yeah. Containing X minus A. So that UA intersection VA empty. Okay. So now if we consider this all possible UAs, so this forms an open cover of A. So we add the finite subcover. So let A is equal to union of AR is equal to 1 to N. Okay. So this implies what? So this implies, so okay. So okay. So now if we consider intersection VAI, I is the one for that A, then this of course contains B, and if we call this W, then sorry. So and W contains A, and of course by choice this intersection VAI intersection WMD. So yeah, so that's that. So that's the proof. Okay. So now, okay. So I shall back into some minutes. So, so this question, sorry. So, consider so let f takes to y continuous, x compact and y house to. Then if it's closed, how to do this? So the proof is the following: x compact y house drop. So continuous is closed now. So we'll start the closest. So let v a closed set in x. Okay. What we need to check? We need to check that if v is closed in my right. Okay. So v is closed. Okay, say v is closed. Now look, since v is a closed set and x compact, so this is what? V is compact. The same argument that we have used in order to prove the homeomorphism, right? So this implies f of v is compact. So and y house dot. So sorry. So this is what? This implies f of v plus y. This implies what? F is a closed map, right? So this is the argument. Okay. So no. Let's go to the next problem. Yeah. Uh, Show that if y is compact, then the first coordinate projection map is closed map. So so y is compact. I'm going to check the first coordinate projection map is closed map. So, how to do, or what are the ways to solve this? So, I mean, anyway, so you can, it can be done in many ways, but till now, whatever you're done using this, it can be solved. Okay. So first try yourself. But and if you are unable to solve, then please let me know in the next live session. Okay. So, so okay, so let's try first assume this thing there was called the first quadrant to this question. So assuming this, let's try the next problem. And it's not a, it's not just a it's a theorem actually. So let f of x to y be a map such that y compact Hausdorff. Then f is continuous if and only if the graph of f is closed in x plus y. What is the graph of a graph of x means all order of the form x comma fx where x belongs. So y is given to be compact house. So then if it's contained in the graph of is closed, okay. So how to prove in graph of growth x cross y, okay. So let yeah. So let us continue. Okay. So define a map H from x cross y to y cross y with x comma y goes to fx comma y. So H is also continuous, obviously, and since y is Hausdorff, so the diagonal of y is closed in y. So this means what? So this implies H inverse diagonal of y closed in x plus y, and what is the H diagonal of y? This contains all limits of the form x comma fx, such that x belongs to x. So this is nothing but a graph of f. Okay. So this is what graph of f is closed in x cross y if f is continuous. Okay. So now, so the one, so for the converse side. So now assume graph of f is continuous in x plus y. So now, so we need to check what? We need to check this continuous. So we basically need to show that f inverse v is closed for any closed v is also y. So Now observe that. So suppose this is x and suppose this is this graph. Okay. So now suppose V is here. Okay. And this is image of it. Okay. So what this strip gives? This strip is nothing but pi to inverse of B, right? And if we take this part, I mean this part is what? This part pi to inverse B intersection graph of F, and if you take the first coordinate projection, pi of this will be F inverse of B, right? So at least from immediate class, so basically the claim is that F inverse V is equal to pi 1 of pi to inverse V intersection graph of F. Okay. So, and I mean, from picture it is clear, but anyway, it can be proved in direct set theoretic manner. But anyway, we are not right now getting into this discussion. But anyway, so F inverse B is equal to pi 1 pi inverse B to the graph of F. We assumed V is closed, so V closed. We have assumed so pi continuous, so pi to inverse V closed in x plus y, and graph F closed. We assume you know what pi to inverse V intersection graph F closed x plus y, and y is compact. So this implies pi 1 closed map. So pi 1 of pi to inverse B intersection graph of F is close to x. So this implies what? So this implies F inverse. This thing close to x. Okay. So this is what it is. So we proved that if we map then y compared how to x continuous if on our left graph of x close to x plus y. Okay. So so these are the more or less the basics of compounds. So now, okay, so I should backward 2 minutes. Oh well. Oh well. So yeah, okay. Yeah. So there are some important theorems which we shall look into the next session. So in metric space, any state is compact if and only if it is closed and totally bounded, and in case of real Euclidean particle but n, they compact if and only closed plus bounded. So this is known as the Heine-Borel theorem, and so basically what? So this implies what? Any state of the closed will be compact, closed and bounded. Okay, so yeah, is compact, right? And of course, open zero one not compact because it's an if and only statement. Okay, so okay, and also one more important theorem which we will shall see in the next session. Suppose f(x) to a continuous, x compact, y water topology, then f attains its extremas. That is, there exists PD in x such that fc less than equal to fc less than fd for x belongs to n. Okay, so these are some important theorems we will look in the next session. Okay, so it's okay, so it's the time to stop here. Okay, we shall meet in the next session. If you have any doubt, you can ask me in the next session. You can email me. I shall get back to you. Okay, thank you. I'm leaving the call.